Hi, everybody. So in this particular video, we're going to try to answer a previous question I posed, which is if you know that the image of a bunch of basis vectors under the transformation spans the corresponding range of that transformation, is it a basis? So if we already know it spans it, we need to know, is it linearly independent? We don't know that because you've seen before that sometimes it's independent, sometimes it's dependent. We don't know. So in order to answer that question, we actually answer a bunch of different topics all at once. They all are intertwined ideas. We talk about the kernel and range of a transformation, the nullity and its rank. We talk about one-to-one and onto-ness. And finally, we get to the question of when does a transformation have an inverse? Again, these are all very intertwined ideas. That's why it's all in one section. It's a lot of notation though. So just basic definitions first. If you have a transformation going from V to W, vector spaces, the kernel of T is the set of all vectors in V that get mapped by T to the zero vector in W. The range of T, denoted the range of T, is just the set of all vectors in W that are images of vectors in V. So you need some examples of this. Let's suppose you just give me any old matrix as M by N, and let T be the core, T of sub A being the corresponding matrix transformation, going from Rn to Rm, defined by just normal matrix multiplication, A times X. In this case, the kernel of this transformation is just all the vectors X, so that A times X is 0. That would be the null space of the matrix. The range of this transformation is all the possible outputs of A times X. That's just the column space. So we have this nice correspondence. The kernel of A and the null space of a matrix, they're the same thing if you have a matrix transformation. And the range of the transformation and the column space of A, they're the same thing also. Again, if you have a matrix transformation. But you need examples that are not like that. You need examples that are not like that. So let's go look at a few. Let's find the kernel and range of this linear transformation. To do so, a good way to start is just to apply the transformation to a generic vector in the space V. So in this case, a polynomial of degree 3 or less. That'd be A plus BX plus CX squared plus DX cubed. As we know, those vectors span P3. So then the derivative is going to be B plus 2CX plus 3DX cubed, X squared. Notice, though, that means that B, C, and D can be anything. So because of that, you can get any single possible polynomial of degree 2 or less. So the range of this transformation is just P2. It's just every single possible polynomial of degree 2. But the kernel, though, of this transformation would not be. The only way to get something in the kernel is if this was 0. If that's 0, because 1x and x squared is a basis for P2, or at least they're linearly independent, we know then B would have to equal 2C, would have to equal 3D, which would equal 0. That means B, C, and D all have to be 0. But the only thing we don't know about is A. So this implies then the kernel has to be all the polynomials, which are just the polynomial A, such that A is a real number. And if you need to, it's literally just spanned by the vector 1. That's it. Pretty easy. Let's try another one. Let's find out what would this guy's kernel of the range be. So once again, in order to figure out how to do a problem like this, a good idea is to just go ahead and perform the transformation on a generic object in the vector space V and to see what it becomes in the codomain W. So this will then be, let's take T of something in P1, so that's A plus BX. That would then be the integration from 0 to 1 of A plus BX. And just skipping the integration, that would have to be A plus B over 2. Right away, then you can tell that the range of D is actually just all real numbers. The reason is that this could be anything you want. B then could be anything else you like also. We just make B be 0. And if you want to get any possible real number, just make A be that real number, make B be 0, and that would be the corresponding polynomial. It's actually just the constant function. The integration of the constant function from 0 to 1 will give you the real number you want. So the range is everything. But at least in the codomain, it's the set of all real numbers. The kernel, though, it's a little more fun. The kernel is so that this is actually equal to 0. That can only be true if B was negative 2a. So the kernel would be the set of all polynomials of degree 1 or less that has the form of a constant. Then I'd have minus b, which is, well, plus b, which is minus 2a times x. And that's where a is just some real number. But that's just spanned by the vector 1 minus 2x. Just take a times that and you get the original target vector. That's it. That's the span. It's just this. That's the kernel. It's the span of that one vector. Easy. Easy. A little more interesting. Let's go and find the kernel range of this transformation, where it takes a matrix and returns the matrix minus its transpose. Okay. Once again, the best way to do these kind of problems is just to find what the transformation does to a generic element in the domain and find out what it maps to in the codomain, and then from there rip things apart. So I'll take the transformation to a generic 2x2, which is A, B, B, C. By doing the subtraction as described by the operation, I get this matrix. Notice that is written as that. You can write it as that linear combination. Right away, then, you can tell that the range, being the set of all possible outputs, is just the span of that one matrix, 0, 1, negative 1, 0. In order to find the kernel, though, it's a little more fun. To find the kernel, I have to set this equal to 0. The only way that could be true is if b minus c is 0, which means b must be c. So the only limitation on the matrix for the input to be in the kernel is that b and c must be the same. So therefore, the kernel being all the matrices, so that the transformation gets mapped to 0, that'd be all the matrices of the form A, B, B, D, but that's the span of these three vectors. And notice, by the way, those are linearly independent also. That's it. Neat, right? Simple. I believe that's enough for that video.